Hi, everybody. So, today I have the pleasure of talking to you about a subject that I like a lot. That is what I do my research on here, and I'm excited to talk to you a bit about graph theory today. So, uh, this isn't. I mean, you aren't going to be tested on this or anything. This week's quiz is on the subject of the compound interest and retirement savings. Next week's quiz, which is our last week of the semester, is on consumer debt. So that's the credit card loans and or credit card debt and installment loans section. And yeah, so this is really just for those of you who are interested in this kind of in other areas of math. This is definitely one of a very applicable area of math in the sense that although I very much like pure mathematics, there are a lot of applied graph theorists out there doing things like city planning, working for social networks, all sorts of things. We'll talk about just some of the huge array of applications that this theory has, and talk about some fun, more modern research. I know a lot of the things that we've talked about are quite modern. I mean, one would expect it from a textbook called Excursions in Modern Mathematics. But yeah, this is really an exciting area, I think. So, what's the plan for today? Today I will tell you first what is a graph. Second, I will talk about some interesting applications. Third, I'm gonna give a motivating example for really like how did graph theory come about. So some interesting applications, and those interesting applications will lead into the origin of the theory. And then finally we'll talk about Euler circuits and paths, which you'll find out what these things are. Good. So let's just jump right into it. Our first question: what is a graph? So this is a big question, and there are lots of really every graph theorist would have a different way of motivating the theory here. But I'm gonna tell you a definition of a graph, which is very different actually than the one I was taught, in the hopes that it can help you see just what's going on here. These are more than just pretty pictures, and I think a lot of people like graphs just for the puzzle nature of them, but they really do they mean things. They mean things in real life, and so I'm gonna define them to motivate that. So, what is a graph? So before I give you a definition, I'm just gonna start going through it. So I'm gonna say we start with a set of objects. We call this the vertex set. Okay, so the first bit of a graph is what we call the vertex set V. Okay. And now the idea, so on its own, we can represent this set V as just the objects. So maybe we say, say V is just the set of, I don't know, let's try just doing 1, 2, 3, 4, and 5. Just the first 5 numbers. Any set of things. These could be apples, these could be numbers. objects. So these could be numbers, people, points, anything. Okay. And then what we're going to do with this is we're just going to pair up elements from this set. We start with a set of objects, call this the vertex set V. Then we make pairs from the elements of V and call a set of pairs the edge set E. Okay? So this whole making pairs business is something that we've been doing quite a lot this semester, actually. We've talked about how many ways you can make pairs. We've talked a lot about, so recall, we talked a lot about how to make pairs of objects. When were we doing that? We were doing that in the voting sections. Good. And so if you remember, there are what we call v_choose_2 pairs here. So that's the number of things you have in your set times that number minus 1 divided by 2. And so here's an example. Say E is the set of pairs. I don't know. So we're just taking pairs from 1, 2, 3, 4, and 5. So maybe we'll have the pair 1, 2, and then the pair 2, 3, and then the pair 3, 4, and then the pair 4, 5, and let's add a couple more. The pair 5 and 1, and the pair, I don't know, 1 and 3. Now, one thing that you might notice is that, or ask yourself, is does the order matter in these pairs? And that actually depends on the kind of graph. Because really, we just make graphs to solve problems. These are a problem-solving tool. I should write that. What is a graph? Well, a graph is just a problem-solving tool. In the sense that it's a way of visualizing a problem to simplify it and see a solution more easily. So here's what we have. So say E is that, and remember we had V being the set of just 1, 2, 3, 4, 5. Okay, and so we can draw this. We can draw this and see it visually. We can visualize this pair of sets. So that's G as V comma E, right? Where V is our vertex set and E is our edge set. This is how we represent a graph right there. And here's how we're going to draw it. Let's just put our vertices 1, 2, 3, 4, and 5 in a circle going around, right? And then for every pair that we have, and I'll draw little circles around these. Okay. So then for every pair that we have in our edge set here, 1, 2 is going to correspond, so why don't I do this? I'll erase these little blue lines, and I'll say that 1, 2 is going to correspond to this edge right here. We just draw an edge between 1 and 2, right? Yes. And then again, we're going to draw an edge between 2 and 3. Maybe I'll make that one blue. And then we're going to just connect all of the dots. So other than that, we do 3 and 4. 4 and 5 make a pair. 5 and 1 make a pair. And then 1 and 3 make a pair too. And so this is our graph. We can call this G, and we use an equal sign to literally mean that this is our pair. This is our vertex set, 1, 2, 3, 4, 5. And this is our edge set, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, and 1, 3. Yeah, so really that's the idea behind a graph. That's the reason that we made them in particular, is to study this system of pairing up objects, and simplify that question of pairing up objects to make it easier to visualize. So good. So in terms of questions about order, does order matter of the vertex? Whether we put one first and 2 second, or whether we do, like, what if we had 2, 1 in there? Well, wouldn't that have given us the same edge? Yes, in this case it would. We're for all of our intents and purposes, we're going to think of these graphs as being what we call undirected. So that means that order doesn't matter. Our graphs will be undirected, i.e., order of the pairs does not matter. If it did, we could draw a little edge saying 1, 2, so then 1, 2, we could draw a little arrow to show that 1 comes first and 2 goes second. And then we could do an arrow from 2 to 3 to show that 2 comes first and 3 comes second. And then if we also had 2, 1 in our thing, in our edge set, then we could do another edge going back, and that would be different. But for our intents and purposes, I won't do it like that. Good. Okay. Here, let me, this is no longer red. It should be. Good. Okay, so let's move along from this to another motivating example. Why don't I just say, I'll just make a note here that we can draw this again as just points. If we didn't want to think about what the numbers were in our set, and we just wanted to think about more abstractly a set of things, and they're paired up in such a way that it looks like this. So that's fine. And if you want, you could notice that this is actually what we call isomorphic to a thing that looks like a house. So, yeah, kind of fun. We can redraw these things, and their properties, their abstract properties, will remain the same. So, let's talk about a few applications. So the first one I guess I'll talk about is social networks. We have a vertex set. V is the users of a social network. And then the pair, the edge set, E, is pairs of users representing, I don't know, say, representing a connection. Say friends on Facebook. So in this sense, you could have like Abby, Becky, Cal, and Dave. We'll call them A, B, C, and D. And let's say that Abby and Becky are friends. Or why don't I say it like this? Abby is friends with all three. Callum is only friends with Abby. And Becky and Dave are friends. So just from this information, we could make a graph, a very simple one, but it's very much like the ones that Facebook uses in its algorithms. We'll talk a little bit more about algorithms later today. That will be fun. So why don't I add that up here? Algorithms. Okay. And so in this sense, we could represent these as just like A, B, C, and D. I don't need to draw them in a circle. I could also draw them in a path. But because I don't know how this graph is going to look yet, I want to draw it in a circle because I think that that's a pretty straightforward way of visualizing. I mean, if you don't know what a graph's going to look like, probably the nicest way is to put them all in a circle. But let's just see. So Abby is friends with all three. So we're going to draw lines from Abby to Dave, and from Abby to Callum, and from Abby to Becky. And then we say Callum is only friends with Abby. So my edge is still just this one. Why don't I make it blue? But it's the same edge, right? And then maybe in green, say that Becky and Dave are also friends. Okay, so now we've got an edge going across there from Becky to Dave. Make that darker. Okay. And now we've got a friendship graph. So this gives us our friendship graph. I don't know. I just made that up. Friendship graph. Doop, 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 doop. Doop, 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 and doop. Now, one thing you'll notice maybe is that if you're looking for a nice way to draw the graph, like I said, drawing them in a circle often works out nicely. But in this case, this could be slightly confusing. If you showed someone this graph and they said, well, what happens there where the two edges cross over? And you think, oh man, I didn't actually want that to look like there was a relationship there, like there's another friend right there at the center. So then you think about it and you think, oh, well, I could actually redraw this if I put Callum on top and then I put Abby below, and then I put Dave and Becky over here. Now I can draw it where the edges don't cross over each other. Right? And so this little sign means isomorphic. But we won't worry so much about that word. Okay. And so there we get a graph of our friends. Oops. Good. Okay, so a second application. This one was quite exciting. Second application to cartography. coloring maps. So this was solved very recently, actually, like in the past 20 years or so. Recently solved is this problem. Any map can be colored with only 4 colors without having countries which share a border colored the same. Okay, so this is called the 4-color problem. It's a pretty self-explanatory name, and so as an example, this is kind of what I'm talking about. So say we had a map. There's our big square map, and it's divided into countries, say like this and like this, and like this, and maybe there's a big ocean. I don't know, a big sea. Maybe it's like this and goes like this. And maybe this one meets right there at the corner. And say this is your country. Alright, and so the idea is that for a long time everybody just kept noticing that every single map you could color like this. So here, I'll show you what I mean. Let's just start going. So we'll try and do it with as few colors as possible. Okay, so there's 1, and then let's do red for all of the ones that, well, for the next one, because we can't do green on that one. And now we can't do green or red on this next one to the right, but we could do red again on this one, say. And that's just fine. We could also do green again on this one, say. And that's just fine. But now we're a little stuck because this one borders both green and red. So all 3 of the ones we have left border on both the green and red countries. And so we'll make another one. Let's do orange for this one. And orange for, say, this one. And then finally we can do blue, say, for this last one, and we've done it. Oops. So the idea here is that it's generally pretty easy to find a coloring, but the hard bit was proving that you could do this. It is generally easy to find a way to color a map with 4 colors. Try it. But proving that it was always possible was very difficult. And so here's what we're actually going to do. Here is how graph theory plays in. The problem was simplified 2. Okay, now we're going to see. So let me copy and paste this map. Copy. And paste. And so what I'm going to do is I'm going to draw a vertex in the middle of every state. So that means that each country is going to become a vertex. So that is the vertex set is the set of countries, or enclosed areas on a map. And the edge set is going to be pairs of countries which share a border. And so what does this look like visually? Well, what this looks like is we're going to draw an edge between this one and this one. We'll make it a little thicker. Draw an edge between that one and that one because they share a border. Draw an edge between that one and that one. They share a border. Draw an edge between this one and this one because they share a border, and similarly with that one, and it also shares a border with this one. And then these two share a border, and these two share a border. Notice that every time we connect these, our black lines cross over a border exactly once. Pretty cool. And then these ones share a border. These ones share a border. And these ones do. And these ones do. So yeah, they don't have to cross over the lines exactly once, but if we didn't draw straight lines for our graph, then they would. So now let's check. This country borders on 1, 2, 3, 4 countries. Sorry, this one borders on 1, 2, 3, 4 countries, and we have 1, 2, 3, 4 edges coming out of it. This one borders on 2 countries, here and here. We have 2 edges coming out of it. This one borders on 1, 2, 3, 4 countries, and we have 1, 2, 3, 4 edges. This one borders on 1, 2, 3 countries, but we've only drawn 2 of the edges. So good thing we checked here, because we forgot this one. Okay. And then this one borders on 1, 2, 3, and this one borders on 1, 2, 3. Now, what I'm going to do is I'm actually just going to erase the graph behind it, the map behind it, and what we'll be left with is a simplified version. Of our map. Isn't that cool? So this is our graph. Actually, maybe I should copy it, and here's what I'm going to do. I'm going to resize it, move it down, move it over here. Okay, then I'm going to copy it. I'm going to paste it over here. Scale that down. And then I'm going to delete all of the things like I was before. Very carefully so as not to delete my graph. Okay. And so there it is. This, our map has turned into a graph that looks like this. Good. So that's the idea of how this can help simplify a problem. And we use there's some deep theory that goes into this. I said this definitely wasn't an easy proof, so I won't go into it. We use computer. There was lots of computer computers used and algorithms and things like this. But the idea here is that we can color now, instead of coloring the countries, we're coloring vertices. So now we color the vertices and ensure that no two connected vertices. I'm going to use this shorthand for vertices, VXS. No two connected vertices are the same color. Okay, so I'm going to stop there, and then I'm going to start again on Euler.